Welcome. Let's dive into one of the absolute cornerstones of calculus, the derivative. Now that word might sound a little intimidating, but at its heart, it's actually pretty simple. It's the language of change. And once you get it, you unlock a totally new way of seeing the world.
So think about this for a second. How do you measure something that's constantly changing, but at a single frozen moment in time? I mean, your car's speedometer tells you your speed right now, not your average speed over the last 10 minutes. How does it even do that? Or how can a company figure out the exact number of things to sell to get the absolute maximum profit? You think these are just, philosophical questions, right? Well, they actually have a concrete mathematical answer.
And to get to that answer, here's our game plan. First, we're going to figure out what a derivative even is intuitively. Then we'll get the basic building blocks down, see how to combine them with some really powerful rules, tackle the famous or infamous chain rule, and then finally, we'll see why any of this matters in the real world.
Okay, so first things first. What is a derivative? Let's just forget all the scary formulas for a minute and build this whole idea up from something really simple. Just walking on a hill.
That's it. Seriously, that's the whole secret. A derivative is just a fancy word for steepness. It's a tool that measures how fast something is changing at one specific single instant. And that's the key. We're not talking about average steepness over a mile. We're talking about the steepness right under your feet, right now.
So picture it. You're walking on a big, curvy hill. When you're huffing and puffing your way uphill, that's a positive slope. When it gets easier and you're heading downhill, that's a negative slope. And what about when you get to the very peak of the hill or the very bottom of a valley and there's that one perfectly flat spot? Well, right there, the slope is just zero.
Okay, so in the world of math, our hill is just the graph of a function. The derivative is like this magical second function, let's call it a steepness finder, that tells you the slope at any point you want on that hill. So if our hill is the graph of x squared, its derivative is just 2x. So what? Well, now you can ask, hey, how steep is the hill when x is 3? Easy, just plug it in. 2 times 3 is 6. The slope is 6. How about when x is negative 2? The slope is negative 4. It's like having a perfect guide for your hike.
Now, you're going to see this written a couple of different ways, so just a quick heads up. You'll see f prime of x, which we just say as f prime of x, and you'll see dy over dx. They look totally different, I know, but don't let it fool you. They mean the exact same thing. We're finding the derivative. We're finding the steepness.
All right, now that we've got the big idea, let's learn the basic building blocks. Before we can tackle some crazy, complex hill, we need to know the fundamental shapes. These are the absolute essentials you're going to use over and over and over again.
And look how simple some of these are. The derivative of a constant, like the number 5, is just 0, which makes perfect sense, right? Its graph is just a flat horizontal line, so its steepness is always 0. Now the most important one here, the one to really remember, is the power rule. For x to any power, you just bring that power down in front and then subtract 1 from the exponent. Easy. Now we've got a few others like how sine becomes cosine, and my personal favorite, this amazing number e, whose function e to the x is its own derivative.
Okay, but let's be real. Functions rarely live all by themselves. They get added, multiplied, and divided all the time. So now we need a toolkit, a set of rules for handling these more interesting combinations.
And the first rule is the friendliest one of the bunch. If you've got functions just added or subtracted together, you just take the derivative of each piece one by one. It's really that simple. It's kind of like calculating a grocery bill. You just add up the costs of each item on its own.
But what happens when functions are multiplied? Now you might think you can just multiply their derivatives, but nope. Unfortunately, it doesn't work that way. We need a special tool for this one, the product rule.
And here's the easiest way to remember it. Forget the formal, mathy-looking formula for a second, and just burn this phrase into your brain. You take the derivative of the first part and multiply it by the second part, just leaving it alone. Then you add the first part, leaving it alone, multiplied by the derivative of the second. It's a simple little pattern once you get it down.
Okay, next up in our toolkit is the rule for division. When you've got one function sitting on top of another in a fraction, we need something called the quotient rule. Now, this one can look a little scary, I'll admit, but there's a fantastic little trick to remembering it.
And here it is. This little rhyme is your absolute best friend for the quotient rule. Low-D high just means the bottom function, the low one, times the derivative of the top one. High-D low is the top one times the derivative of the bottom. So just say it a few times.
Low D high minus high D low over the square of what's below. You'll never forget it.
All right, we have saved the most powerful and yeah, sometimes the most challenging tool for last. This is what we use for functions that are nested inside of other functions. This is the mighty chain rule. And the absolute best way to picture what's happening here is with one of those Russian nesting dolls. You know, you've got the big outer doll, that's our outside function, and when you open it up, there's a smaller doll inside. That's our inside function. The chain rule is just our method for dealing with this kind of structure.
And here's the recipe, broken down into 3 easy steps. First, you take the derivative of the outside doll and you pretend the inside doll is just one solid thing. You leave it completely alone. Don't touch it. Then, as your final step, you multiply that whole result by the derivative of that little inside doll. That's it. Work from the outside, then deal with the inside.
So, we've built our whole toolkit. We get the idea of steepness. But who cares? What's the payoff? Why does any of this actually matter outside of a math class? Well, this is where it all comes together and gets really cool.
Hey, remember that flat spot on our hill, the one with 0 slope? That's the whole key. Derivatives let us find the exact peak or the exact valley of any function. In the business world, they call this optimization. It's literally how companies find their maximum possible profit, or their minimum operating cost. And in physics, well, it's the language of motion itself.
So here it is. This is the secret sauce. If you want to find the highest or lowest point of anything you can possibly graph, you find its derivative and you set it equal to 0. You are just asking the question, where is the hill flat? Because those flat spots are always at the very top or the very bottom. This simple little equation is one of the most powerful ideas in all of science and economics.
And this shows you that direct connection to motion. Your car's velocity is the derivative of its position. It's just the instantaneous rate of change of where you are. And acceleration? That's just the derivative of your velocity. It's the rate of change of the rate of change. Calculus is literally the physics of movement.
So from the slope of a hill to the peak of a company's profit curve, all the way to the acceleration of a rocket, the derivative is the hidden engine powering our understanding of a world that is always in motion. It really is the language of change. So the only question left is, what change in your world would you want to measure?